So good afternoon and thank you all for joining on a Saturday. So, just to do a quick recap, we have been discussing, both Professor Mishra and Professor Naik have been discussing problems where we have some sort of entity to manage or disburse. And we have to give it to a set of candidates, and candidates have preferences and options. And this could be a static option or a dynamic option. They also discussed that the outcome of a choice may be deterministic, like we have been doing now, or it can be probabilistic, or it can be competitive. Like we are disbursing land, or we are trying to decide on a budget, or we are trying to decide on a policy where there is a certain set of resource entity to be managed. Now, here, as we said, that these are all top-down algorithms. And yesterday he discussed certain bottom-up methods also. So just to do a quick recap of what we are trying to do before we go to our algorithms, is that there are candidates who give their preferences and options, and each option is the choice for the resource manager or the central top-down manager to try and figure out what should I do, which option should I select. And once we have done this, now we have determined that if I select the first candidate, then if I select the first candidate and he says or she says that I will give a revenue of X, but it could not be fixed. The actual revenue may be less than X, more than X. So the outcome may not be deterministic as we have been solving now. Secondly, is that among the bidders, there can be collaboration and competition. For example, in the bids, other than everybody saying that I will do this, there could be choices given where somebody says I alone will do this. Then they say that along with somebody else I will do this. So there could be combinations of options. That means I could form groups, subgroups for solving that same problem. What we have started solving is something different. At least we have seen a basic method. Then there could be, as we said, that even in this there are multiple objectives which we shall discuss. Then there are questions of layered parties, and there could be issues where we are required to come up with a fast solution I need the solution quickly. You cannot start running an algorithm for hours at end and come up with a solution. For example, I need to bid for my auction. So till now, the algorithms that we have developed are working for the top-down manager to do the selection. What will it be? What will the algorithms be for individual parties? If they have to provide sequential bets, or the other day, yesterday, Professor Nayak talked about bottom-up. That means now instead of there being a central agency deciding who else will combine for this resource, the parties start interacting with each other, and therefore the whole algorithm, instead of being a centralized algorithm, which is now, to distributed algorithm. And then I said there are multiple parties who interact with each other into forming a distributed algorithm. So these are the interesting and important dynamics and issues that we want to discuss. However, as we have said, that in order to proceed further, we need to go step by step. Having looked at the basic search or design space, it is also called search method, or it is also called a design space exploration method. What are the options? Which options should I choose? What should I do? Etc. etc. Having seen the basic 5-step algorithm that we saw last day, what were those 5 steps? Initialize. Can anybody help me?
Goal test, expand, and continue.
Very good. Thank you. And now we will see how we modify those when we want to come to real time, when we have to handle multiple objectives, how we look at the search space, what do we do with it, etc. etc. Then subsequently we will look at when complete information is not available. Subsequently we will look at if you take a decision, your outcome is not fixed. Then we will see when there are more than one competitive parties, what do you do? All in this same framework. But here we have not used one aspect. We have not yet used ML. That means we have not used machine learning, or we have not yet done anything by which large data of past results is used to solve these problems better. That we have not yet done. We will discuss those options because those are the things that you will start doing as you proceed. But the other day he was talking about, looking at rainfall, water, etc., etc. How will you decide an economic policy? Or how will you decide a simple thing of how much of various kinds of opportunities you will give to different groups in your affirmative action? All of you understand affirmative action? Affirmative action is like saying that those who are having income less than this, they will definitely get so much percentage priority for so much percentage of the resource. Because I have a longer term goal of alleviating the poverty. So these are various, because somebody asked me the other day, can we look at exploration? Can we look at, certain strategic options for affirmative action. So design space exploration also helps us do what is called a what if analysis. Can anybody tell me how do we model what if analysis in our current state space? What if I do this at this point in time? What will happen? Where do we model our what if options? Anybody? Yes.
Sir, by selecting different nodes to expand.
Yeah. So in our exactly, you're right. So it is in the state transformation rules, right?
Yes, sir.
The what if analysis is incorporated in the state transformation rules. So all these problems we are mapping into this whole concept of a state or a configuration, state transformation rules, which gives me my whole configuration space to explore. Are you getting, all of you getting some idea of how we are trying to bring all kinds of these problems into this single framework of configuration, state transformation rules, and this configuration space, which we will explore? Is that getting a little clear? Palkit Lohia, are you there? Pradeepti Thakur, are you there? Priyanka, are you there?
Yes, sir.
Are you getting an idea of what I'm saying?
Yes, sir.
Okay, good. So our objective is, given a real life problem, we will try to frame it into this state transformation rule, configuration space, and the exploration problem. And then the exploration consists of these 5 steps. Systematically, we will explore this configuration space. Now, how we explore, what we explore, depends on our goal. What is our objective? The last day, we saw basic algorithms to resolve that objective. Now, we are going to look at 2 more directions, that those algorithms, the algorithm A star, which we saw yesterday, typically requires a lot of space and a lot of time. But if that space and time is available, the first solution is optimal. And we solved it for minimization and maximization problems. So now we start looking at other aspects. So just a quick recap. Our modeling, which we take from a real life problem, we convert it into a state space configuration, where other than the other things which we just talked about, the concept of heuristics is very important. We saw some examples of heuristics last day, and then are the algorithms. So other than the state space definition, heuristics and algorithms. And the single framework for the algorithm which we saw is initialize, select, goal test, expand, and continue. Anybody has any questions now? Does anybody have any question? Please let me know. Ritesh Kumar, any question? Divyansh Gupta, are you there? My goodness, nobody's there. Gaurav, Meena, are you there?
Yes, sir.
Any questions till now? Gaurav?
No, sir.
Jai Krishna?
No, sir. No doubts.
Okay. So now, this algorithm, we know that for minimization problems, we required a lower bound heuristic or an underestimate, and for maximization problems, we required a lower bound heuristic, and for maximization problems, we required an upper bound heuristic. And the suitable node that we took out from the list open was either the minimum FN or the maximum FN. That is how we did, and then we updated the cost. But though algorithm A star terminates with optimal cost as the first solution, the problem is that you don't have a solution till it really terminates, till it finds the first solution. And therefore, there are cases where it may take a long time and memory to come up with a first, or here in that case, only or optimal solution. So we are looking at algorithms we work in limited time and limited memory. And limited time algorithms are of two kinds. One of them is called an anytime algorithm. The other is called a contract algorithm. The anytime algorithm works like this, that the algorithm runs, it is finding one solution, then a better solution, then a better solution, and an anytime algorithm can be stopped at any point in time. Whereas a contract algorithm, you predetermine a fixed amount of time. You say, I will give you 5 minutes to solve the problem. Anytime algorithm, you say you start, I'll tell you when to stop. And contract algorithm, a predetermined time is allotted. So there is a slight difference. You cannot stop a contract algorithm before its predetermined time. So now we will see, and then we will also notice that this open list and closed list, what do we do by discarding and redoing nodes in open or closed lists by discarding or redoing nodes in open or closed lists to handle memory constraints. So this is what we will see. There are millions of such algorithms. We will see only those which are basic. And if you want to see advanced algorithms, then we have to spend some more other time. So the first algorithm is called anytime DFS or anytime depth first search. Here, open is maintained as a stack. All of you know what is a stack? What is a stack data structure? What is a stack data structure?
Sir, last in, first out.
Last in, first out. Good. So the node that is selected from open is select the first node in open. Previously in A star, open was a priority queue. That means open was sorted by the FN values, either minimally or maximally. Then again, if open is empty, then obviously you terminate. But in DFS, when you reach the first goal here, then what you do is, because you have reached one goal, it is not guaranteed to be optimal. First goal is not guaranteed to be optimal. So what you do is you maintain a current best cost, current best solution, which you initialize at the beginning, saying that I don't have any solution. If it is a minimization problem, you keep it at infinity. If it is a maximization problem, you keep it at minus infinity. Therefore, whenever you get a goal, you check. What do you check? Can anybody tell me whether this solution is what?
Optimal or not?
No, not optimal. Whether this solution is
Is better than current.
So
better than
that we have to make minus.
let us call this current best. Better than CB. If so, what do we do? Update. Update. What do we update?
Our CB.
Update CB. Correct, correct. Update CB. Is everybody with me?
Yes, sir.
Good, good. This part is the same. This part is the same. But here you can also come to a node in open, or you can also come to a node in closed with lower cost. So all that you manage. So only these two things we do. We select the first node in open, and here when we put all these nodes in open, put nodes in the front of open, right? Open is a stack. Put all these new nodes in the front of open. Is everybody with me? Anybody who is having a doubt? Vaishnavi? Any doubt?
No, sir.
Okay.
No, sir.
So now let us do an example that will make it clear, because now we will get a sequential set of solutions. So we now come to our old problem with heuristics. So we have our open list. So we initialize current best to infinity. It's a problem which, so let us initialize current best. So current best is infinity. This is our iteration. This is our, sorry, iteration we can keep smaller. Iteration. This is our open list. And this is our closed list. In some cases, people don't maintain a closed list. So this is optional in DFS. So as to, why is this optional? So as to save
Memory.
memory. Perfect. Very good. You all have got the hang of it. So initialize current best to infinity. In iteration 1, open contains A, closed is empty. What is the F value of A? 0 plus 6, 6. Which node is removed from open?
A.
A.
And A is put in closed. Which nodes are put in open now?
BCD.
BCD.
D. Now it is put in a particular order. Which order you put B, C and D matters. Well, you can put B, C, D or C, D, B, whichever, but you will maintain some ordering. Now it is a stack. So B with cost. What is the F value of B?
15.
What is the F value of C?
16.
What is the F value of D?
8.
8.
So
Now in the yes.
the order we decide, like
We decide locally decide. Huh?
Yes, sir.
We could have put D first, C. Let us assume some random order we are using now. Correct? Are you all with me?
Yes, sir.
Now, which node will be removed?
B.
Very good. B will be removed. When B is removed, what is put in the open list?
EFG.
In front
EFG.
of the list, right?
Yes, sir.
Yes.
And what will be the value of E?
27.
What will be the value of node F?
20.
No. Yeah, 20. Correct. And what will be the F value of node G?
17.
Everybody is with me? Simon, are you there?
Yes, sir.
Okay, you're in sync.
Yes, sir. Yes, sir.
Which node will be removed?
E.
So A was here, B. Now E will be removed. What will be put in open?
IJ.
Wait, let me do something. I will require some more. Okay. So I, what will be the F value of I?
36.
J,
32.
so A, B, E, F will be 20, G will be 17, C will be 16, D will be 8. Everybody fine? Which node will be now removed?
I.
Okay. Once I is removed, what is the property of I?
It's the goal state.
It is the goal state. Once it is the goal state, what is the first thing that will be done?
Sir, check if it is better than the current best.
The current best is infinity, so the current best will now become
36.
6. Now open list will be J, sorry. Which node will be removed?
Sir, J.
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 What will happen to current best?
CB will change to 32.
Now which node will be removed?
F.
F will be removed. And what will be put in open?
E, I, G.
Are you coming to E with smaller cost or larger cost?
Sir,
With a larger cost.
So you do nothing to E unless you have thrown away closed. If you had thrown away closed, you would have had to regenerate E. But since you have not thrown away closed, then let us look at these two options because this part is very important. If you don't throw away closed, then you don't do anything because you have come to it with a larger G. What about node G? Are you coming to it with a smaller G or larger G?
With a larger G.
So again, you do nothing. Node I? You're coming with a smaller G or larger G?
Smaller.
Smaller. Now you're coming to node I with a smaller G, but what is the new value of that node I? New F value?
So 35.
And what is the property of 35?
It's less than what we
It is greater
like.
than the
It's greater than the current best.
perfect. Perfect. So though you have come to node I with cost 35, you prune that node. Because it is greater than the current best. So we go back to our algorithm, select the first node in open, discard Fn if, sorry, discard if Fn is worse than current best. Correct? So we remove this node. Now you have G17, C16, and D8. This is A, B, E, I, J, F. Now which node will be removed?
G.
G.
G. When G is removed, what happens to J? Which node is put in open now?
H, J or H.
Yeah. So J or NH. So J is put in open. So J has got F value how much?
19.
20.
20.
20.
And H has got how much?
30.
30.
And C has got 16. D has got 8.
Hello, sir.
Yes.
Sir, in the last one, the G was 17. While we have added the heuristic also like 1. So it for G it will be 16 plus 3 19 now, or 17 plus 3 20.
20. You are right. Here somewhere we made a mistake. G will be 20
Like-
everywhere, है ना?
No, sir. But here the G is 17 above 1, and after
Yeah.
that we
For
have
node G, the F value will be 20, na? Sorry. No, the F value, sorry.
Sir, for H it will be 33.
H, it will be 33.
T.
What were you saying?
so like
See,
sir.
This
For-
G, it had come 16 plus H value was 1, so it was 17. G is all right. G, the path cost to G is 10 plus 6, 16, and its H value is 1.
Yes, sir. So, sir, for J, sir, it will be 16 plus 3, 19 plus 0. So, it will be 19, not 20.
19.
Yes, sir. It will be 19.
It will be 19. Correct.
And, sir, for H, it will be 32.
For H.
It will be 32.
Yes, sir.
How much? Where does it come from?
So, from
16?
G plus 16.
16 plus 3 plus 3, 32. Thank you.
Yes, sir.
Good. Now, which node will be removed?
Sir, the J.
J. Again, I have got another path. So again, I am getting B, E, I, J, F, G, new J. And what is this J? What will I do after I remove it?
So, we will change the CB.
CB will now become
19.
and the new nodes will be H 32, C 16, D 8. What will I do to H now?
Like we will remove, but we will not get the goal.
No, wait. H is removed because from here going to H is of no use, no? H is 32 this way. So I will discard H.
Yes, sir, got it.
Now which node will I remove?
The C1.
I will remove C. So let us continue this side. So I will remove C, and what will be generated?
F and G.
And if you come to F, are you coming with smaller cost or larger cost? You are coming with
larger cost. Yes, sir.
And to G also you are coming with smaller cost or larger cost?
With the larger cost.
So nothing to be done?
Yes, sir.
What will now be in open?
So only D.
Correct. Now from D I will generate what? So D will now go to closed. I'm not writing everything.
G and H.
Right. Now G, it will come to G with cost how much?
So 12.
And H?
So 9, 12. Yeah, both of them 12.
In next step, I will remove G and what will come? J.
J.
J will come and J will come with cost 14. H will be with 12. G will go to closed. Then after this, in the next 13th iteration, what will happen?
The CV will change to 14.
Yes, CB will change to 14. There will only be H with 12 and the closed list. And H has got no children, correct?
Yes, sir.
Yes, sir.
So in the step 15, open will become
Empty.
sorry, this is step number 13. This is step number 14. Open will become empty and we will
Terminate.
now. Does anybody have a doubt?
Sir, here in the stack we put the nodes randomly. So
Yeah. If you had put it in another order, let us say we had put it in an order by ordering the ones with Fn, then you would have got DCB before BCD, right? You would have got it in the beginning. You would have got DCB.
yes, sir.
And then you can see that if you did it that way, you would have reached 14 earlier. Correct?
Yes, sir.
Because you would have got just imagine, you would have got DCB, then you would have got HG, then from H nothing would come, then from G J would come, and you would have got 14. And once you get 14, all other nodes will start getting, because B and C are of 16 and 15, nah?
Yes, sir.
They will get thrown out.
Yes, sir.
So, as you have already pointed out, the DFS sorry, very good point. Depends. I purposely did that long painstaking way on order in which we insert the children. So as you just pointed out, Pankuri, that it would be good to look at the children generated, sort them by the FN values and then put them in open, right?
Yes, sir.
Good. You are all getting the hang. So good idea is to sort the children generated by Fn and then insert in the beginning of open. Very good. So that is why this algorithm is said to be directional. This does not guarantee that by sorting it this way, it will always give you the first solution as optimal. But as you just pointed out, it gives a better idea. Any other point? Good. Let us proceed. Do this as an assignment, all of you. later on. But can you tell me what is the problem with DFS? Okay, we'll come to that a little later. Yeah, tell me.
Sir, if the tree grows larger and larger, then it will keep on penetrating to the very deep.
So
and
if the tree is larger in one direction and the solutions lie in another direction, then we are in trouble, right? That's what you're saying.
yes, sir.
Yes, yes, yes. So remember that. Has everybody understood what is the problem with DFS?
Yes, sir.
The problem with DFS is if the tree is like this here and the solutions lie somewhere here, then DFS potentially goes too deep down. Useless paths. Is that clear? Suryansh Kumar?
Yes, sir, it's clear.
Good, good, good. Now what we do is, what was the difference between DFS and A-star? How do we bridge the algorithm of A-star on one side and DFS on the other side? But DFS is anytime. You can stop it anytime. So people, what they do is they quickly try to find an approximate solution and create the first current best. So you have a solution before you start, it may be very bad. Some approximation solution. And then you start DFS. So whenever you stop, you are stopping with some solution. But how do you bridge the gap between DFS and A-star? What algorithm would you do? Anybody has an idea? Somajit? Yeah, who was saying? Tell.
Sir, actually in the A-star, sir, we will get the optimal solution in the first like when we will get, but in the DFS we will not get. So I will choose A-star.
Yeah, but A-star may require more memory, and it is not an any time algorithm. It is not a limited time algorithm. In A-star,
we could try iterative deepening.
We'll come to iterative deepening, but there is another variation to do.
But sir, DFS will take more time.
Huh?
So DFS will may take more time as compared to
DFS will, that part we will solve. That part we will solve. We'll solve. Like Shivam said, we'll use another method called iterative deepening. Iterative
breadth first, sir.
No, breadth first search. So what we do is, what is MDFS? MDFS says keep the first M nodes. Can anybody complete? Sorted by
their F value.
Perfect. When M is 1, it is normal DFS. When M is the full list, then it becomes
A-star.
A-star. And this MDFS will give you the bridge. Like Pankhuri just mentioned, we sort the children by first by FN and then insert into the list. What you could do is you could insert these elements and have a parameter M and keep the first M element sorted. Now sorting of a constant number of elements is constant time. It does not take much time. If that m is a constant 20, 30, 5, 10. On the other hand, if you have to sort 1 million nodes, then again you need a lot of data structure. But sorting the first few elements is not important, not a problem. So if you now apply MDFS, has everybody got an idea of what MDFS is?
Could you please repeat?
Gaurav, yes or no?
Yes, sir. Could you please repeat it? Like I didn't get the point.
Okay. Okay. Rajapati Yashwant Rajsai, are you there? Rapati Yashwant Rajsai, are you there?
Yes, sir. Yes, sir.
Are you following, no?
I'm catching up, sir. Yes.
So now, if we do, let us say 3DFS. So if we do 3DFS, open, closed, CB and iteration step. So initially CB is infinity, step 1, open is A, closed is null. And here we have 6. In step 2, what will now open be?
BCD.
No, you are going to do 3DFS. 3DFS means the first 3 are sorted.
DBC,
D8, B
B 15,
15 and
and
C.
C 16.
Now this is the same as what Pankhuri had mentioned, local sorting. Now next, in the next iteration, which will be removed?
D.
D,
D will be removed. And what will be put in open?
I like so G and H, but they are
G
both,
and H. And where will G and H come? In which order?
so they are both F equal F.
Equal, so any order, that is fine. 12, H12, B15, C16. And so on and so forth. You all can complete it?
yes, sir.
Now for a larger tree, you can see as you vary this M, it will move closer and closer to A star. And what it shows is that an appropriate choice of M is a good controller of memory as well as the first solution and the order in which solutions are obtained. So when the state spaces are very large, a reasonably good constant M value is a very appropriate solution. Got it?
Sir, one thing, sir. That sir, if we will just like or sort the 3-1, then sir, only we have to sort the that children, or we will sort all the 4 like in the third step.
We will, if our M is 20 and we have generated 4 children, then
Yes,
we will sort these 4 and the remaining first 16 elements of open.
Okay, so all of them.
Yeah. So that we are not stuck up with a local direction. Got it, Akshat?
Yes, sir. So, sir, here, sir, after sir G will go, then J will come, then it will become 14. Like F will become 14. Then what will we do? We will put the G in the back and put.
G will go into closed, yes.
And sir, what will happen with J? J will come here and it will have the F14. So we will change the order, like we will put the H in front and then J.
Yes, we'll put H in front. Yes. So let's complete it. Let's complete it.
Yes, sir.
Since you have a doubt, let's complete it. In the next step, which will be removed?
So G.
G,
G will be removed. What will be put into open? How will open look like now? We are doing 3 DFS.
Yes.
Clear?
Yes, sir.
Now what will be removed?
H, but it will not have.
There is no children, so J will be 14 and 14, 15, 16. If it was 14, 16, 15, then it would have been reversed. But we'll sort the first 3 elements of the list. Now what will be removed?
So J will be removed.
What will happen to CB?
It will change to 14.
And then what will happen to B? What will happen to C?
Yes, sir.
And then what will happen?
Like, sir, we have CB is 14 and B is 15 and 16. So,
So
it
they
will
will be all removed, taken out and removed.
Yeah, they will.
Got it now?
Yes, sir, got it.
Very good. Anybody else has a doubt?
So for that initial like starting and nodes, don't we have to solve the whole array?
I can't hear you, Gaurav.
Am I audible?
No, you're audible, but some sound is coming, but it's all garbled. Can others hear him properly?
No, sir.
You type in the chat box, huh, Gaurav?
Okay.
Let's move on. So now what is iterative deepening? As we just saw that this is the problem with depth first search. This being a problem with depth first search, then we have to ensure that we don't go step down. So what iterative deepening does is this. Other than current best, it creates a new concept called cutoff. And it performs DFS with a cutoff. Two cases may arise. One, no solution found. Then we terminate. Second, it can do DFS, MDFS, whatever it wants to do. If solution is not found, then it updates what? What does it update?
CB.
Cutoff.
Okay, cutoff, sorry.
So it updates cutoff. What is the advantage? That this problem, which we had thought will not happen because this will be cutoff 1. By doing this, it will not get a solution. Then it will apply cutoff 2. Then it may not get a solution. Then it will apply cutoff 3. Then it will get a solution. So the potential problem of going deep down in a gorge in a search gorge will not happen. So in iterative deepening, it will make some initial cutoff. Now this choice of cutoff is a very critical thing, which we shall discuss a little later, but it will make some cutoff. And by choosing this cutoff intelligently, iteration after iteration, we will prevent ourselves from going into a deep gorge. The only thing is that after one cutoff and no solution is found, we restart. So I have a problem with redoing re-expansions, which means I have a problem with redoing things again and again. But at least I don't have this problem. So if I can intelligently select cutoffs, I may be doing very well. So now I combine MDFS with cutoffs. Is it clear to everybody? Idea? Dhruv Joshi, are you there?
Yes, sir.
Clear?
This is, sir, I have confusion. What is cutoff here?
I'll come to it. So what we initially decide is what is my cutoff? That is my big question. Good question. What is the obvious cutoff in this problem? First cutoff?
So the F value of the first node.
F value of the first node. So your cutoff must be greater than equal to F value of the first node. So your cutoff will definitely be the first cutoff will be greater than equal to F of S. So choose some cutoff. Tell me some cutoff. Anybody?
8.
Don't choose 14. Tell me some cutoff.
8.
8. Let us choose our first cutoff as 8. And I'm applying one normal DFS. So I will look at which node? Nodes seen, nodes expanded, and nodes backtracked. So which nodes will be expanded? A will be expanded. Will B be expanded?
No, sir.
No. So B will be backtracked from. C will be expanded or backtracked?
Backtracked.
D will be expanded or backtracked?
Expanded.
Then from D I come to G. G will be expanded or backtracked?
Backtrack.
H will be expanded or backtracked?
Backtrack.
So I have not found a solution with cutoff 8. Now from which nodes will I try to find my next cutoff?
Sir, backtracked ones.
Backtracked ones. Is everybody clear? Next cutoff is found from backtracked nodes of previous cutoff. So what are my cutoffs? B was 15, C was 16, G was 12, and H was 12. Correct? Obviously, I need not select any node below 12. And it may not, unless I really want to become adventurous, I don't need to select anything above 16. So select as a cutoff. Is everybody clear that I have to select something between after 12 and preferably before 16?
So why before 16?
Not necessarily. I said preferably.
Okay,
You
sir.
can select more. You can select any other cutoff, but at least not below 12. Is that clear, Akshat?
Yes, sir.
So tell me what you want to select.
So 14.
Let us select 13. Okay.
Okay, sir.
Let us select 13. If we select 13, then we'll get an idea of an iteration. Is everybody with me? Anybody lost? Is anybody lost? Gaurav, in your question for getting initial M nodes of open initial, there is only one node in open list. No?
No, but am I audible?
No. I'll come to it. So now let us say we start all over again. So again, which node? A is expanded. Is B backtracked or expanded?
Backtracked.
C?
Backtracked.
D?
Expanded.
G?
Expanded.
H?
Expanded.
J?
Expanded.
No,
No,
13.
sorry,
J
sorry,
ka to
sorry.
14 hai.
Yeah, sorry.
Backtracked. So now I have 16, sorry, 15, 16, 14. Now I'll give a cutoff, say 15. Then what will happen? What will be expanded? A. B will be expanded or backtracked?
Expanded.
Then from B I will generate E, F, G. They will all be expanded or backtracked?
Backtracked.
Then C will be expanded or backtracked?
Backtracked.
D will be expanded.
Yes,
G
sir.
will be expanded. H will be expanded. J will be expanded. And I will find a solution of cost 40. Then I will stop. Because in the previous iteration I did not find. In this iteration I have found by a depth first search. Whichever depth first search I have used. Now I have used a simple depth first search. I could have used any MDFS. Is the algorithm now clear?
Yes, sir.
And now you can see why I said that that problem is not taken care of. Now taken care of. So my preferred algorithm under control, my preferred anytime algorithm is iterative MDFS. Now there are various ways to control the next cutoffs. One algorithm which always selects the minimum node in the backtracked set as the new cutoff. So there is an algorithm called IDA star whose strategy is new cutoff is the minimum for minimization problems. Fn from backtracked set for minimization problems. whenever it gets the first solution, it can stop. Is this clear now? So preferred algorithm, there are other algorithms. There are many other algorithms for anytime search. For anytime search. One of them are called PAC algorithms. But I don't want to discuss all that because our objective is not to go into too many nitty-gritty algorithms, but to give you an idea, because we have to remember our objective is economics problem to state space representation to a search algorithm. We have to always remember this. An economics optimization or design space exploration problem goes to a state space definition, goes to a search algorithm. And we are talking about an anytime algorithm. And we have seen DFS, MDFS, and iterative MDFS. All right. So we have discussed the properties of these algorithms, and I don't want to go to it now. Let us come to what are contract algorithms. We won't go into too much of, yes, any questions?
Yes, sir. So in the last one, sir, can you just open that slide? Sir, if we have reached the J, then sir, are we storing the from which parent node it had came?
Yes. Every time you are going to store, every time in the search algorithm, you will always store the best parent.
Then sir,
we
what's the
discussed the other
difference between A star? Then in A star also we are storing. So
yes.
It will take the memory also. IDS will also take the same memory.
No. In A star, the number of nodes expanded, that open list size is big. For every node in the open list, what do you store? You are going to store the GN, the FN, the HN, and the parent of N. So that is just a constant. That is just a constant with every node. It is the number of nodes in that open plus closed list which causes the problem.
Okay.
So coming to contract algorithms, so I'll give you a fixed contract. So the contract algorithms are a sort of what are called greedy beam algorithms. What do? They say at every iteration, keep only top R nodes in open and keep rest of the nodes in suspended, and create another list. And what you do is, at any point in the search, you have got only R nodes in open. If this is the total open, let us say. So you keep the best R nodes and keep them in open. And the rest of the nodes, you push them to suspended. And again, you select some node in open and go for some time, and then again, as soon as open overflows, you put the overflowed nodes in suspended. And when you finish, when your time is over, you stop with whatever you have. If open becomes empty, then you bring back from suspended. If open becomes empty and we still have time left, bring back the best nodes from suspended. Otherwise, if time is over, terminate with best solution till now. So what you do is you cut open, and last time we were sorting the few nodes in open. Now you just keep these R nodes and throw away the rest of the nodes into suspended. And you go on doing this after some time, every time you flush some nodes from open to suspended, and you calculate this R based on your tree structure. So your algorithm typically proceeds like this. And these all go into suspended. And you calculate R given a contract time or nodes. From a contract time T, you compute how many nodes you can see. And from those nodes, you try to estimate this D1, D2, D3, D4, such that this size, and you choose an appropriate R.
So we are changing R every time.
You can change. You can keep R fixed for a given contract also. R can be dynamic, but typically normally beam search keeps a fixed beam size for the whole contract period.
Okay, sir.
But you choose the beam search given your contract size and your understanding of the problem. How deep is the search tree, etc., etc. It's a little tricky to do it, but you can do a calculation. So contract algorithms are those where the time is given a priori. From the time given to you, you first estimate how many nodes you can examine. Now you, looking at your total search tree's depth D, you break it up into how many layers you want to break it up. And for those layers, you try to make searches of same size in every layer. But so you cut after you have searched level 1, you decide on, so you know that I can do 50 levels. I have got 50 levels. I will do them in 5 such layers. So first layer I will do something. So I can expand maybe 1,000, 50,000 nodes. So I will expand 5,000 nodes in every round. Now for every round, I will do this. Then I will choose the top B elements. Then again I will do 10,000. Then again I will do 10,000 and so on and so forth. So this is how I do. If by chance it becomes empty, then I use suspended list. Otherwise, that is why it is called beam search. This is my original search tree. That is why it is called a beam search, because it tries to focus on a beam and goes down. There are many variants of beam search. Beam search does not guarantee optimal solutions, but it is a very practically useful algorithm. Any questions? Anybody has any questions? Gajala, Rushi, Rian, any questions?
So could you please explain this with an example, like how we
I have to
do?
draw a big example then, no?
Okay, sir. Sorry.
You work out, it will come conceptually. If you understand it, it will come. Now we come, if there are no questions, Jai Krishna, any questions till now?
No, sir, none as of now.
So now we come, after having looked at limited memory, limited time, we now see how we adapt to multi-objective. So let us say our traveling salesperson problem or any other multi-objective problem. There are two costs on the edges, 5 and 8. Or there will be another option of a cost, 6 and 7. So the first parameter is time and the second parameter is cost, let us say. In multi-objective optimization, you typically have conflicting and non-commensurate costs. That means your objective functions are typically conflicting. If you try to go faster, you will incur more cost. If you want to do in less cost, you will take more time. Secondly, these objectives are conflicting and non-commensurate. What do you mean by non-commensurate? Can anybody help me? Dhruv Joshi? Dhruv, what is
Yes, sir.
non-commensurate? Any idea? Sunidhi, any idea what is non-commensurate? Naitik Goel, are you there? Aryan Singh? Ananya Parikh? Has everybody left? Should I stop? If nobody is there in class, what is the point for me to continue?
So is it non-complementing solution?
No, first answer. Gyan Ranjan Pradhan, are you there?
Yes, sir.
So what is non-commensurate? What is commensurate and non-commensurate? Non-commensurate means they cannot easily be combined into a single objective. You know, sometimes I give W1 into cost 1 plus W2 into cost 2. They're like apples and oranges. I really cannot combine them. Is that clear? Utkarsh?
Yes, sir.
Now what we have here is very interesting. So on every edge, we have a set of multiple multi-objective weights. Previously, Because it was a single objective, if you have two costs, obviously you will take the smaller one. But now if you have one cost saying 6, 7, another cost saying 5, 8, you cannot throw away. Because we will have to keep which set we discussed this name? Which set? Non-dominated set. Every node has a set of multiple what? Multi-objective?
Yes, sir.
What? What? One is costs and weights. What is the other?
Heuristics.
Yes. Now I cannot have a single heuristic estimate, no? Have you seen how my same problem is getting a little more complicated now?
Yes, sir.
And my solutions will be a set of
Non-dominated.
right. Very good. Now that I have this, I will go back to my algorithm. I will now have open and closed. Again, the F values at the open and close. So how will I? So I have got at every node, Gn is a set. Hn is a set, isn't it?
Yes, sir.
So Gn will be some x1, x2, sorry, x1, y1, sorry. For two objectives, x2, y2, and so on and so forth up to xn, yn. Hn will be some h1, t1, h2, t2, hm, tm. It will be like this, no, at every node.
Yes, sir.
How to compute f? No?
All combinations and then find the non-dominated set.
Perfect. Perfect, Tushar. Non-dom xi plus hi, comma yi plus ti. Has everybody understood?
Yes.
Yes, sir.
Non-dom of this. So now every Fn is like that. Now, which node to remove from open? Because now there is no unique minimum or unique best node in open. There is no unique best node in open.
So maybe we should take the ratio. Will it work?
No, we have to remove, at least we have to remove a non-dom node, isn't it? Now non-dom node and non-dom value are different things. A node is said to be non-dominated if it contains at least one Fn value which is not dominated by every other node in open. It's a very complicated definition. This non-dom value, a non-dom node is something. And then you put it back. And then do you terminate at first solution? Because as soon as you get a solution, your solution is a set, isn't it? Even if you reach a goal node will give you a set of options, correct? Are you all with me?
Yes, sir.
Yes, sir.
So, solution is a set. Let that solution set be S, current solution set. Call it CS. When you reach a new goal node, G, it will have a solution set SG. So how will you update CS now?
Union and non-dominated?
Yes, non-dom, very good. Non-dom of CS union SG. Has everybody understood? Naitik Goel, are you there?
Sir, I am not getting what is a non-dom.
Did you not understand earlier? See, look at this 6, 7 and 5, 8. Look, let me explain again. 6, 7, 5, 8. Suppose I gave you another solution, which is 10, 9. What does it say? It takes 10 units of time and 900 rupees cost. Is it clear now?
Yes, sir.
What this means? Now tell me, is 10, 9 better than 6, 8 or worse than 6, 8?
Sir, depending upon the
Worse
sir,
than-
minimum maximization.
Minimization. We are doing minimization.
Then sir, it will worst.
Worst. Is it worse or better than 5, 8?
So it is worse.
Is 5, 8 better than 6, 7?
Sir, can't say.
Can't say. So if it is worse, we say if an element is dominated by any other element, we say it is dominated. An element which is not dominated by any other element is said to be non-dominated. Have you understood?
Yes, sir, I got.
So now it is a non-dominated. So we always maintain non-dominated sets. The whole comparison in mathematics, you studied non-dominated sets in a different terminology. Do you know what you studied it as? What sort of sets? Remember?
No, sir, I don't.
Have you all studied partial order sets? Integers are totally ordered. It's a linear ordering. But when you have got a pair of values, then you have partial ordering. You create what are called lattices and other types of structures in math. That is all right. Anyway, don't need to study so much, get so confused. But now let us understand how. Now have you understood how we are computing F as a non-dominated set of xi plus hi, comma yi plus ti?
Yes, sir, I got it.
And how you are doing CS union SG as non-dominated set?
Yes, sir.
Shomajit? Shomajit,
Yes,
are
sir.
you there?
Yes, sir.
Got
I
it.
got it. Yes, sir.
Sir,
Huh.
in Fn, shouldn't it be xi plus hj? Like it doesn't have to be corresponding, right?
Yeah. You're right. Xi plus hi dashed, yi plus ti dashed. Some ti dash, double dash plus ti triple dash, you know, all combinations. You're right, exactly. Perfect. You are all getting the math right now. Who asked this?
So that was me, Adhiraj.
Good. You are concentrating. Do you have a relative studying in IIT?
No, sir.
Because my last student was Aditya Rastogi, so I was worried. I was interested to find out if you are related to him. So now you can rewrite the whole. Now are you clear that the same pattern of these 5 steps? Initialize, select, goal test,
Sir?
expand, coordinate.
Sir, can you explain this part again? How have you generated the non-dominated set?
Okay, I'll explain. Let me explain. Suppose I have a set of elements x1, y1, x2, y2, xn, yn. Let this be S. Can anybody tell me how I will find non-dom S?
So
Shivam,
maybe,
you only tell me how you will find non-dom S.
Sir, by taking all the elements which are strictly whose both of whose elements are strictly less than others.
Not strictly less, it could be equal, whatever.
Okay.
So non-dom S is some Pi, some Xi, some, let us say, Pi Qi, such that Pi Qi is an element of S and there does not exist R J Mj element of S such that
Rj more than Pi and Mj more
P
than
is
Rj, sorry, very good. You're not getting the hang of it. Rj greater than Pi and Mj greater than.
QI.
This is when both are being maximized. But if one is maximized, one is minimized, then this is if both objectives are maximized. Otherwise, you have to the relation. Have you now understood how this happens?
Yes, sir.
Shiva?
This part is clear. Sir, I wasn't getting the part where we considered all the possibilities of adding heuristics.
So in heuristics, so now I have a node whose GN is 5, 8, sorry, 6, 7, and its HN is 2, 4, 1, 5. Is that clear, Shubham?
Yes, sir.
So what does it mean? I can have a solution of cost 5.8 and I can have another solution of cost 6.7. I can come, right? And it also
Yes, sir.
tells me that I can go here with a solution of 2.4 or I can go with a solution of 1.5. This is the G values and these are the H values. Samjha?
हाँ, sir.
Now you do all combinations. 5.8 added to 2.4, 5.8 added to 1.5, 6.7 added to 2.4 and 6.7 added to 1.5 and find the non-dominated set. क्या आता है? What is now G plus H? What are my options? What do I get? 7, 12.
7, 12, 6, 13,
Then
8, 11,
then
7, 12.
what is my non-dominated set? 7, 12, 6, 13, 8, 11. Again.
Yes, sir.
Clear to everybody else?
Yes, sir.
Yes, sir.
So those 5 steps are now adapted by non-dominance, nothing else. Then you apply DFS, A star, MDFS, iterative MDFS. You can write, you can make bread omelette, you can make tinku, you can make whatever types of food you want with this. This is how you simply solve the problem of multi-objective search and come up with a final set of non-dominated solutions, which is also called the what front? Chalega? Any other doubt?
No, sir.
Vitthal Agarwal, are you there?
Yes, Professor.
Are you able to more or less gather what is being said?
Yes, sir, I'm able to understand.
Now, there are many ways of doing ordering. I don't want to confuse you. But now, basically, we have done 2 things. If you want to run an A star also, if you want to run a traditional algorithm, then you can give the ordering. You can always say that I will sort my open in vector order which I call K ordering. That means if I get 5, 7 and 4, 8, I will first sort it by the first one and then sort it by the second one. So if I do this K ordering, in any case, a non-dominated element will be in front. So there are many ways of doing ordering. To put it back into the normal A star paradigm or DFS paradigm, you can actually sort it by a dictionary order. That means you can vectorize this and sort the vectors first by the first. If there are ties, then by the second. If there are ties, then by the third. This sort of linearization works, but you have to remember that this linearization is not a total order. It does not mean if A is before B, A is better than B. It is just an implementation issue. There are other methods, but I will, not go so much into them now. But are you getting tired? You want to stop or you want to continue just another 10-15 minutes?
Sir, I have one doubt, sir.
Uh-huh.
Sir, when we will find the last one in this yes sir optimal front, when we will find the last one like our solution, then it will contain a lot of it may contain a lot of non-dominating. So sir, how to decide whether which will be the right answer?
Correct. This is a good question. A Pareto optimal front is like this. The last day which we said is that you ask somebody for, take a meal option. You have 5 or 6 criteria for meals. So you will provide the Pareto optimal set. The user who has asked you to solve the problem will now try to look at the set and decide. As we said the other day, if you could combine the objectives before solving the problem, then you would combine it into a single objective. But what happens after this is called a preferential choice. From solutions. Now, for the same problem, there may be 5 people wanting solutions to this problem. You will provide the Pareto optimal set to them. Each of them will have their own way of choosing which one is better for them. You remember the other problem the other day, Professor Nayak and Professor Mishra was saying that while there are many solutions to the same problem, different solutions are preferred for different farmers. Correct?
Yes, sir.
So when somebody asks you for a solution, when 10 people ask you for a solution, they first don't know what solutions can come. So you will give them the non-dominated set. Now each of them, using their personal preferential choice, will choose which option they can get. This is how you solve the preferential choice problem that Professor Mishra was mentioning the other day. Got it, Akshay?
Yes, sir, got it.
Are you relating how we are using all this to solve the economics problems? But we have a solid algorithmic and mathematical background.
Yes, sir.
So there are other things. I think you all will get too tired if I go more. We'll stop today. There are other things, evolutionary algorithms and or graphs and all that. We'll do it some other day. So just let me repeat again. Our method, see, we have multiple parties. Our method is like this. There is an economics problem. With all its complications, we convert it to what? What?
State space search problem.
Now we have our algorithms. Which are the meta algorithms for all of these problems. Now these are solutions. And here is your user who has given you this problem. You give this solution to the user. The user can again either choose or refine the problem. Saying, no, you combine these two, you do that, you do this, give me this, or can ask another query. or give you more options. All of this will modify the state space. Then again, you'll run the algorithms. What we are studying now are these generic meta algorithms that work for single or multiple objectives. You remember those vague words we started earlier? Dimensions, parties, preferences, etc., etc., etc. And when Professor Nayak yesterday talked about top down and bottom up, these algorithms are top down or bottom up?
Top down.
Yes. So obviously there will also be bottom up algorithm. Interesting, no?
Yes, sir.
Always remember this overall thought process that we have in mind. Always go back to this overall thought process and then we will know exactly what to do. Any questions? Otherwise we can stop the recording.
Sir.
Huh.
Sir, I wanted to ask a question about the DFS part. Sir, if we know prior to running the algorithm that the cost cannot be negative, so can't we just prune after we find out that the G has become greater than the current best F?
Yes, we can. But that always we will do. That we will always do. Whenever you are inserting a new node, if its F value is greater than the current best, you throw it away. Whenever you remove a node from open, if its F value is greater than current best, you throw it away. Those you anyway incorporate in the algorithm. Any other questions? Thank you all, especially the TAs, for spending Saturday on this. And thank you all. Vaishnavi, was it useful or have you gone to sleep?
No, sir, it was useful. I like the class.
No, because I asked you to organize this class because I thought that let us go a little slowly. Then if I went fast, no, anyway, you all will have to read it again to understand. But if I went very fast, nothing would have gone in. Shivam,